There are possibilities just buzzing underneath.
Oh, absolutely. And quantum mechanics kind of says, yeah, you're onto something there.
It's this totally bizarre idea that things, tiny things anyway, can be in multiple states, multiple places at the exact same time.
That's the one. We're talking about quantum superposition. Think of it like a blurry photo before it comes into focus. It's not just one thing yet. It's a mix of possibilities.
Exactly. And that's what we're diving into today. Quantum superposition. We want to unpack this, foundational idea. How can something be in multiple states at once? Why is it so important? And honestly, so weird.
Right. And we're using Your Name's recent analysis as a guide. Quantum superposition, foundations, manifestations, and constraints. It gives a really solid, rigorous look at the whole concept.
Yeah, it's our roadmap for this deep dive. Our mission, really, is to pull out the core ideas, look at the crazy implications, and give you a shortcut to understanding why this is both fascinating and, let's face it, pretty challenging. No getting lost in the super heavy math, hopefully.
Exactly. We want to get to the heart of it because superposition, even though it sounds like sci-fi, it's real. It's fundamental to quantum theory, and it's where a lot of cutting-edge research is happening.
Okay, so multiple states at once. Let's get into that. What does that actually mean on a basic level? How do scientists even describe this?
Okay, yeah. To really get it, we do need to touch on the language quantum mechanics uses, just a bit. Imagine a special kind of mathematical space called a Hilbert space. That's the stage where quantum states live and perform, so to speak.
A stage for quantum states.
Okay.
And what are the performances?
Well, any possible state of a quantum system, think an electron spin or O photons polarization, can be described as a combination, a superposition of simpler fundamental states, like mixing primary colors to get any other shade.
Ah, okay. So you mix these basic states together to get the actual state it's in.
Sort of. The quantum state is that mixture, that superposition. It's not that it could be red or could be blue. It's simultaneously a bit of both in a specific quantum way.
Got it. So it's not just either, it's and.
Precisely. And mathematically, we write this state, let's call it SIE, like this. Is, esia, us.
Whoa, okay, math symbols. Break that down.
Don't worry. Us is just our state, the superposition. The she's things are those fundamental basis states like spin up or spin down, the pure colors in our analogy.
Okay, and the alphas.
Yeah, alphas.
Right, the os. These are numbers, actually complex numbers,
Okay.
that tell us the amplitude or sort of the weight of each basis state in the mix. They're crucial.
So they tell you how much spin up versus spin down is in the superposition. Not exactly how much in a classical sense. It's more about probability. If you actually measure the system, say you measure the electrons spin the square of the absolute value of alpha I, gives you the probability of finding the system in that specific state.
Ah, probability. Okay, that makes more sense, like dice rolls or coin flips.
Kind of, but with a quantum twist we'll get to. And yeah, because it's probability, all those I values have to add up to 1. You're guaranteed 100% to find it in one of the possible states when you measure. That's called normalization.
Right, makes sense. Probabilities add to 1. Now, the analysis we're looking at makes a big deal about this not being a classical mixture. What's the difference? That sounds important.
It's really important. A classical mixture is just, well, ignorance. Imagine you have a bag with red and blue marbles. You pull one out without looking. It is either red or blue, you just don't know which one yet. There's a probability, say 50-50, but the marble itself has a definite color.
Okay, so classical mixtures like, I'm pretty sure it's this or maybe that, but the thing itself is settled.
Exactly. You can describe that with probabilities, maybe using something called a density matrix, where pin is just the plain old probability of it actually being in state theta.
Got it. So how is quantum superposition different?
It's fundamentally different because the system isn't in one definite state before measurement. It's genuinely in that combined state, that superposition. And this quantumness, this coherence between the states in the superposition allows for something amazing. Interference.
Interference, like sound waves canceling out or adding up.
Precisely like that. The probability amplitudes, those alpha I's, can interfere with each other, just like waves. This can lead to outcomes, like in experiments, that you absolutely cannot explain if the system was just in one state or the other, like our classical marble.
Wow. Okay, so the quantumness allows for wave-like behavior even for particles.
You got it. That's the magic or maybe the weirdness of superposition.
So how do we know this is allowed? Is there like a fundamental rule in quantum mechanics that says, yeah, go ahead, mix those states?
There is. It's called the superposition principle. It basically says if you take any two valid quantum states any linear combination of them, meaning you add them together with some weights, those alpha coefficients results in another perfectly valid quantum state, provided it's normalized, of course.
So you can just keep adding quantum possibilities together, like mathematically?
Mathematically, yes. If ERSA and ESO are valid states, then something like Escher plus Urus is also a valid state.
And this isn't just some mathematical trick, it's deep in the theory.
Oh, absolutely. Our source highlights this. It comes from two core ideas in quantum mechanics. First, that states are like vectors in that Hilbert space we mentioned. And second, crucially, the equation that governs how quantum states change over time, the famous Schrödinger equation, is linear.
Linear, meaning if you add two solutions, you get another solution, something like that.
Exactly that. The Schrödinger equation, Eider-Dusche, it tells us how the state order evolves. Because it's linear, if you start with a superposition, say Euros plus Ders, it will evolve into a corresponding superposition later on, like Cauers plus Ters. The superposition persists through time according to the equation.
Okay, so the basic rules allow it, the evolution preserves it. But where do we see it? What's the killer app, the classic demonstration?
Right, the evidence, this is where it gets truly mind-bending. The absolute classic is the double-slit experiment.
Yeah, I've heard of that one. Where particles, like electrons, somehow go through two slits at once. Still sounds impossible.
It feels impossible, but here's what happens. You shoot individual particles, one by one, at a barrier with two narrow slits in it. Behind the barrier, you have a detector screen.
Okay, and you see where they land.
Exactly. Now, if these were tiny bullets, just going through one slit or the other, you'd expect two clumps of hits on the screen right behind the slits.
Makes sense. Two slits, two bands.
But that's not what you see. You see an interference pattern alternating bright and dark bands, just like you'd see if waves were passing through both slits and interfering on the other side.
Even though you sent the particles through one at a time.
One at a time. That's the mind blower. It's as if each individual particle somehow explores both paths simultaneously. It interferes with itself.
So each particle is in a superposition of went through left slit, AND, went through right slit.
That's the standard interpretation, yes. The probability of finding the particle at a certain point on the screen isn't just adding the probabilities for each path. You have to add the amplitudes first.
Those alpha things again.
The amplitude for getting to point X is like amplitude X. Mistake, says it pesos. When you calculate the probability, which is amplitude squared, amplitude X, you get extra terms, interference terms that come from the combination of both paths.
And those terms create the striped pattern.
Exactly. Those interference terms wouldn't be there if the particle only took one definite path. It's direct, observable proof of superposition in action.
Okay, that is undeniably weird. Tiny particles acting like waves, being in two places at once. But what about, bigger things? Could my cat be in a superposition of sleeping on the couch and demanding food? Schrödinger's famous thought experiment, right?
Schrödinger's cat. That thought experiment was designed to highlight exactly this absurdity when you try to scale superposition up. And while quantum mechanics doesn't strictly forbid macroscopic superposition, well, we obviously don't see cats in such states.
Phew. Okay, so why not, if the rules allow it?
In theory, yes. The source material does talk about experiments pushing this boundary, trying to create superpositions in larger, though still microscopic, systems, like a tiny mechanical resonator, basically a vibrating bar put into a state like pros bemol, leftists rights, simultaneously vibrating left and right.
Still tiny, but bigger than an electron. My intuition is screaming no, though. What stops my coffee mug from being in a superposition of on the table and on the floor?
That's the million-dollar question, really, and the main answer physicists give is decoherence.
Decoherence. Sounds like it stops being coherent, stops being quantum.
That's a pretty good way to put it. Decoherence is the process where a quantum system interacts with its environment, the air molecules bouncing off it, photons hitting it, vibrations from the table, everything.
So the universe is constantly bumping into things.
Pretty much. And these interactions act like tiny continuous measurements. The environment effectively finds out which state the system is in, even if we aren't looking. This leaks the quantum information out.
And that destroys the superposition.
It destroys the coherence needed for the superposition to have those distinct quantum effects like interference. The system gets entangled with the environment, and the superposition rapidly decays into what looks like a classical mixture, a definite state, just like our marble example. It chooses a state, you could say, because the environment forces it to.
Okay, so the environment is the enemy of quantum weirdness on a large scale.
For macroscopic objects, absolutely. The interactions are just too numerous and too fast. There are equations, like the Lindblad-Master equation, that try to model this. They basically show that the terms representing the superposition, the off-diagonal terms in the density matrix picture, get suppressed really, really quickly by interaction with the environment.
Is there a way to estimate how quickly?
Yeah, there are formulas for the decoherence timescale. It depends on things like the energy difference between the states in the superposition, the temperature of the environment, T, and how strongly the system couples to that environment. For big objects, where the energy differences between, say, here and over there are significant and coupling is strong, this timescale is incredibly short, like unimaginably fast.
Faster than we could ever notice.
Way faster. That's why your mug stays put. It decoheres into a definite position almost instantaneously.
Okay, decoherence explains why big things look classical. But this sounds related to another quantum puzzle, the measurement problem, right? The source mentions this too.
Yes, they're deeply connected. The measurement problem is this fundamental clash. You have the Schrödinger equation describing this smooth, continuous evolution allowing superpositions. But then, boom, you make a measurement and the system instantly collapses into just one of the possibilities.
Like the superposition bubble just pops.
Kind of, yeah. The standard theory just postulates this collapse happens upon measurement. It's sometimes called the von Neumann postulate. But the Schrödinger equation itself doesn't describe this sudden pop. It's like there are two different sets of rules, one for when we're not looking and one for when we are.
Which feels unsatisfying. What counts as a measurement? Is a consciousness a detector?
Exactly. That's the core of the problem. What constitutes a measurement that causes this collapse? Decoherence helps bridge the gap, showing how interactions look like collapse by suppressing the quantum effects, but it doesn't fully solve the fundamental question of why we only ever experience one outcome.
And this is where those different interpretations of quantum mechanics come in, like many worlds.
Precisely. Interpretations try to resolve this. Many worlds says, no collapse. All possibilities happen, just in different parallel universes. Objective collapse theories say maybe collapse is a real physical process happening spontaneously, especially for large systems. Hidden variable theories suggest maybe superposition is just hiding deeper variables that actually determine the outcome. They all grapple with the meaning of superposition and measurement.
Wow, so superposition isn't just weird, it points to these fundamental questions about reality itself.
Absolutely. And the puzzles don't stop there. The source also brings up relativity. How does Einstein's theory fit with superposition?
Oh man, how does space-time affect this?
Well, when you move to quantum field theory, which combines quantum mechanics and special relativity, things get more complex. Superpositions now involve different configurations of quantum fields spread across spacetime. You have to make sure these superpositions respect causality no faster than light signaling and Lorentz invariance, meaning the laws look the same for different observers. Defining local superpositions and things like entanglement of the vacuum itself, it gets really intricate. It puts further constraints on how superposition can manifest across space and time.
So the universe's own rules about space and speed limit the quantum weirdness too.
Seems that way. So let's recap maybe. Superposition. Fundamental quantum principle. Lets systems be in multiple states at once. We see it directly in things like the Double-Slit experiment causing interference.
Right, but it's fragile, especially for big things.
Yeah.
Decoherence, the interaction with the environment, quickly makes things pick a state, making the world look classical to us.
Exactly. And this whole process is tangled up with the measurement problem. Why do we only see one outcome when we measure? And even has complexities when you bring relativity into the picture.
It feels like superposition isn't just one simple thing, but depends a lot on the context, the system, the environment.
That's a great way to put it. And while decoherence gives us a good picture of how classical behavior emerges, the deep nature of superposition, what happens during measurement, and how far we can push it towards larger scales, these are still huge open questions, very active research areas.
And the drive to control it, like for quantum computing.
Yeah.
That's pushing our understanding too, using superposition to do calculations.
Absolutely. Building quantum computers relies entirely on creating and maintaining these delicate superpositions in qubits, the quantum versions of bits. A qubit can be 0 and 1 at the same time, thanks to superposition. Protecting them from decoherence is the major challenge. Success there could revolutionize computation, materials science, medicine.
So it's not just philosophically weird, it's practically important too. Which leads to maybe a final thought for everyone listening.
Go for it.
If, at the most fundamental level, reality is built on this principle of multiple possibilities existing simultaneously, what does that really say about the definite single world we perceive every day.
Hmm.
Is our solid reality just, like, the result of constant decoherence smoothing out the quantum fuzziness?
That's a profound question to sit with. It really challenges our intuitions about what's real. We definitely encourage you to mull over these strange implications of quantum superposition.
Yeah, maybe think about the quantum possibilities hiding beneath the surface. Thanks for taking this deep dive into the weird world of superposition with us.
Thanks for listening. Keep questioning.